Leo. Very good. So next we have Leopoldo Pando-Zayas from the University of Michigan, and he will tell us about logarithmic corrections to the entropy of ADS black holes. Please, Leo, go ahead.
So thank you very much. Thanks to the organizer. This is clearly a challenging time, and a lot of effort has gone into putting this conference, so thanks a lot. My title is, for some people, self-explanatory, logarithmic corrections to the entropy of black holes. So it goes nicely after Samir's talk. But let me nevertheless motivate a little bit why this is a reasonable and interesting thing to do. So first of all, the Bekenstein-Hawking entropy is very universal, and we all like this formula as sort of a gateway to quantum gravity. But it is so universal that that it might obscure whether your computation of the degrees of freedom or your treatment of the degrees of freedom is really correct. So in the cheesy analogy of black holes being the hydrogen atom of quantum gravity, this is like getting the Bohr energy levels correct, but that doesn't tell you that you know actually how to treat the electron. So you look for corrections to this formula. There are two kinds of corrections that come from treating gravity as an effective field theory. So there are massive fields that you integrate and they give you higher curvature corrections, which here I have denoted as ... There are other kinds of corrections that come from massless fields, and they contribute to this logarithmic correction. So just in a one sentence statement of this talk is, I'm going to explain some of the progress in understanding this particular coefficient, a logarithmic correction to the entropy in the context of ADS-CFT. So we have field theory on one side and gravity on the other. And again, this goes very nicely after Samir's talk. The setup was explained in the context of ADS-CFT. We have two ways to approach this coefficient, and we want to make sure that we understand how to do it and whether it matches or not. So there is, in fact, a long history of using this sort of test to better understand the degrees of freedom behind accounting. So I'm borrowing here from a very, very eloquent review of Ashok Sen. He used this subtitle, an infrared window into UV physics. And the reason is because the coefficient of the logarithmic corrections is determined macroscopically on the gravity side from the massless particle spectrum, and it is somehow insensitive to the UV completion of the theory. So if you compute it in your supergravity and you have this number, and I am a string theorist or a loop quantum gravity person, and I tell you I did my microscopic computation, I can check whether you are correct or not. This is kind of a litmus test. So for any enumeration of quantum black hole microstates, this coefficient that measures some sort of scaling of charges must agree with what the low energy supergravity says. And of course, it has been used by Ashok Sen and collaborators to check various asymptotically flat black holes in string theory and provide a precision test for the Strominger-Vafa counting. This was done by Sen. There are a number of reviews. And this can be done also to challenge loop quantum gravity, also by Ashok. The important thing that I want to highlight is that behind this whole set of computations in asymptotically flat black holes, there is this quantum entropy formula, which essentially is a prescription for computing this coefficient, but it builds up it builds on another formula, which I will discuss. So we would like to have some sort of gadget like the quantum entropy formula for ADS black hole that will tell us how to go about computing these corrections more generally, rather than case by case. Another applications of this sort of approach was presented by this paper here, Pathak, Porfiriadis, Strominger, and Varela, to check a microscopic realization of Kerr-CFT. In the context of ADS-CFT, a very beautiful application was also was in this paper by the Charya, Grassi, Marino, Sen, where they study the free energy of ABGM theory, and in general, you can go for any 3D n = 2 theory. These free energies on the street sphere are usually given exactly by an area function, and you can expand for large N and look at the coefficient, and this coefficient was reproduced in this beautiful paper from 11-dimensional supergravity. So in this talk, you can view this talk as a, or what I'm going to explain as a continuation of this sort of well-respected, let's say, tradition. So this is the outline. I will tell you first a little bit about how to do the microscopic computation for the ABGM theory. But this, again, very quickly, you will see that this is true for a large class of 3D n equal to Chern-Simons matter theory, but my focus is always basically logarithmic correction. So I have to go beyond large N. I will then describe the gravity macroscopic computation. And after that, of course, I will turn to the n equal 4 superconformal index, where we can essentially try to run the same script. In this case, because we would like to have a fairly universal description of how to go about this in the context of the ADS5 black hole, I will also use a version of CFT to estimate these logarithmic corrections. So here's ABGM theory. It was mentioned yesterday by Shiraz, and I think in general is an object that we know. Here's written in n equal 2 language, so it's a quiver with two gauge groups, un plus un, and the Chern-Simons levels are k and minus k. The index that is of relevance here is the topologically twisted index. You can think about it in the Hamiltonian formulation as more or less along the same lines that Samir explained. It's a Witten index with some that you decorate with some charges, flavor charges in this case, and it counts half BPS states. So the formula for any 3D n equal 2 theory, you can write a formula for the index. This formula is obtained by localization. I believe Zaffaroni has given talks at previous strings conference about this subject, but roughly, if you think about ABGM, there are two gauge groups. So you see the contribution for the vector multiplets here in the denominator. Then you have two set of bifundamentals. Once I call A in my quiver diagrams, they contribute to the partition function, to the index like this, and then the B's for 3 and 4, they contribute. So this is now by now a mature subject. So given a 3D n equal 2 field theory, you can compute the index basically algorithmically. What is important is that the evaluation here, you have to sum over some solutions of equations that look like the Bethe-Ansatz equation. So it's called the Bethe-Ansatz approach, but it's very algorithmic. So you solve these equations, you plug the solutions, and you have the index. So one important advantage of this approach is that this is an expression that is exactly in n, granted that you have all the solution of the Bethe-Ansatz equation. So it's very easy to put this in a computer and study numerically, which is what we did. So if you study this in the Larsen limit for k equal 1, so that this is due to ADS4 times 7, the leading piece goes as n to the 3/2, this blue term here, it's very symmetric, and it was obtained by Benini, Christophe, and Zaffaroni in 2015, and that reproduces the Bekenstein-Hawking entropy of the dual magnetically charged black holes in ADS4 cross S7. So Na here, sorry, are magnetic charges, and delta are their chemical potential, but you have to, there's an extremization procedure. Again, this is all sort of background. The key important result is that when you compute this index on field theory, you get these logarithmic corrections. Again, this was obtained with my colleague Jim Liu and student Vimal Rati and Wenli Zhao, who's now a PhD student at Princeton and had a very nice paper today. So this, in fact, as I was explaining, this I can do more generally for a large class of Chern-Simons matter theories. I'm interested, of course, in those that have known supergravity duals. So I can essentially think of replacing the 7-dimensional sphere by any Sasaki-Einstein's 7 manifold. There's a list here of explicit examples that we worked out in this paper with Yushin. And for all of them, you get that the logarithmic term is minus a half log of n. So the natural question at this point is, of course, can we reproduce this coefficient from the gravity side? From the gravity side, you have a black hole, some background, some gravitational background, and you're interested in quadratic fluctuations around those background. Once you integrate those, you end up with essentially a computation of determinants. In the context of a curve space, of course, a very efficient way that is respects to some extent diffeomorphic invariance is to use the Higgs kernel expansion. So you can write these determinants, in terms of the Higgs kernel, which again, this is roughly a way to think about it, but it contains also information about zero modes. So you have to be very careful and subtract the zero modes. And another important fact is that this Higgs kernel admits a Sealy DeWitt expansion for a small tau, but because in this talk we are interested in logarithmic terms, you see that all I really care about is the terms from the Higgs kernel here that are tau independent, because the logarithmic part is already going to come from this term. So I am interested in a particular Sealy DeWitt coefficient, which would be n equals d over 2. So then, because of these operators are usually Laplace-like operator or maybe Dirac operator, but they are kinetic operators, it is natural to also think of this parameter as rescaling naturally. And this is, you can see how the scaling structure enters into the answer. So the final answer is essentially a formula of this type. So the Sealy DeWitt coefficient of d over 2, and then subtract the zero modes. And of course, you still have to add the zero modes as appropriate. Now, on very general grounds, this coefficient vanishes in odd-dimensional spaces. There can be contributions, subtle contribution for boundary, but in general, from bulk, it will be zero, just because you cannot write the right curvature invariant of a given weight. So I guess for some people, this is known as the integrated trace anomaly. This is mathematically the same object, but you can see that the origin is slightly different here. I'm thinking of, I have a theory with some scaling defined, and I'm looking at the coefficient as that scale change. All right, so let me just finish this very quick introduction. Again, this is all very standard. There are many books that help you compute these kind of contributions. But the key facts that I want to highlight is that the coefficient of the log is independent. That coefficient is independent of the cutoff. You can change your cutoff and that number will not change. In odd-dimensional spaces, and we are interested in 11-dimensional supergravity, the log can only come from zero modes, okay, on boundary modes. So what we need to do to compute the partition function is to subtract the zero modes, because you counted them using the Higgs kernel, and then add them appropriately with this beta, which essentially explain how to the appropriate integration for the zero modes, and then of course consider the Gauss contribution. So let me, so let me very briefly explain what the result is. So there's a two-form zero mode in ADS4. There's more generally, well, there's a two-form zero mode in ADS4, and that two-form zero mode contribute to the ghost. You need a series of ghosts to quantize the three form of 11-dimensional supergravity. One of them is a two-form ghost. This is work by Siegel in the 80s, and this is how it contributes to the partition function. So again, this depends on how this beta 2 is how you have to add to form zero mode in 11-dimensional supergravity, and it is essentially 7.5. Many of these computations were performed by Sen in the context that I explained at the beginning, and then you have to count how many zero modes, to form zero modes you have. In this case, there's this subtlety on how to approach the stream of black hole, and you are instructed to approach it through the non-streamer branch. And here's the answer. If you use the ADS-CFT dictionary that relates the scale to the rank of the gauge group, you will see perfect agreement. All right, so this is the computation on the gravity side. It matches nicely the field theory side. Let me explain that this is also the result for the large class of ADS-CFT duals that I explained at the beginning. So for all these Sasaki-Einstein manifold, I obtain on the field theory side the same -1/2. So I have to make sure, or I have to understand how on the gravity side they are the same. So the two form zero mode that contributed came from ADS4. And there was nothing on, well, there was nothing that could contribute on S7. So what I really want to make sure is that there's no one form zero mode in any of these Sasaki-Einstein, because otherwise I will have a contribution coming from the three form in from the three form. But it is established that in 7-dimensional compact Einstein manifold of positive curvatures, all of these all satisfy this property, there is no zero mode. So the first the Laplace of one form's harmonics is bounded. So we immediately get the result for all these spaces.
Just
now,
10-minute
yes.
warning.
Sorry?
Just 10-minute warning. That's all.
Thanks. All right, so I explained this computation for black holes that came from this column, middle column here, for M2 brains probing cone over some Sasaki-Einstein. There are other black holes that you can obtain if you consider an M5 brain wrapping a hyperbolic three manifold. In this case, from the field theory side, you can compute, well, there's a systematic algorithm to compute the field theory, and then there's on top of that, there's the 3D correspondence that maps data in the 3D theory to Son-Chern-Simon invariants, which are known. So you know now the field theory partition function analytically and very clearly, and you can do the computation on the gravity side as along the lines of what I explained. And this essentially gives you this formula that we obtained with Dongmin Gang, Nagwu Kim, and then with Francesco Benini and Dongmin Gang in these two papers. This is a slight generalization. Of course, the scaling of n is slightly different for this kind of supergravity solutions. But you see, B1 here is the first Betti number. So I will have one form zero modes coming from the hyperbolic three manifold, and they will contribute. And G is because I'm considering the theory not on S1 cross S2, but on S1 times an arbitrary Riemann surface of genus G. So this formula, again, was obtained on both sides, this logarithmic correction on the field theory and on the gravity side, and also much. All right, so one thing that I want to explain is that a lot of this work has been done on sort of on case-by-case basis. So there's a ADS-CFT pair, and you compute, and the result agree. But it would be really nice to have something like sense classical entropy function. This is a function. This is a function that basically will give you the Wolf entropy. So this would be the entropy that has all the higher curvature contributions. So this is a very important problem. We still, so there's been some work, of course, in extending that construction of the classical entropy formula in ADS spaces by Morales and Sanleven and Goulart. And recently I reviewed it with Joel Gosch, and currently Joel Gosch, we did ADS4, and ADS5 we are discussing with Joel Gosch and Victor Godet. We think that this is probably a more efficient way to capture the other kind of correction that I have not talked to you about, this higher curvature corrections, but there is still a number of details to work out. The quantum entropy formula of Sen has been very successful for asymptotically flat space. What I have shown to you is that at least for ADS4 black holes, the formula, in fact, does not give you the right answer. The right answer we are getting is by using the full geometry, the ADS4 asymptotic geometry. Let me show you just very briefly. If you take the near horizon geometry of the black hole, you will have a space that is ADS2 cross M9. M9 now would be S2 bundle over S7, and you can run the same computation. Now it's a little bit more involved. There are more zero modes. Generically in ADS2M, you have to inform zero mode. So in ADS2, you will have gravitino zero mode, graviton zero mode, one form zero mode, and then you can form three form zero modes by wedging this one forming ADS2 with the two forming in M9. And the answer is known, was also simultaneously obtained by Gion and Lal, and does not agree with the quantum entropy formula. So we're looking for some sort of big machinery that can help us understand this. In this sense, it was great that there were these developments about the ADS-5 black holes that Samir just explained very beautifully. These three papers started that revolution. In fact, my background is a picture that I use in a Viewpoint article describing this very interesting development, but it has been extended to ADS-4, ADS-6, ADS-7. And one question that we would like to have is, so given that, so we have using ADS-CFT at the, let me go here, using ADS-CFT as an arrow here, we have been able to understand microscopically the entropy of ADS black hole, but perhaps because it's such a universal quantity, there can be alternative approaches to it. So maybe we can take some sort of limit, near horizon limit, Alassane, or maybe Bardeen-Horowitz limit, kind of like Kerr-CFT, and have an explanation for that entropy from this near horizon description. Okay, I will, so this is for the ADS-5 black holes.
Sorry, just 5-minute warning.
Okay, thanks. For the ADS-5 black hole, so there's the index that Samir explained. He also pointed out that in this paper, in a paper with my student Gonzalez Lescano and Hong Liu from Michigan, and my colleague Jim Liu, we explored the index beyond to the logarithmic approximation, which is what we are interested, and we obtained this number. So coefficient is 1. I will not go into the details because there are two approximations Samir already explained. There's the Cardi-like limit, and there's a large n that uses the Bethe-Ansatz approach. But in different ways that we play with the formula, we came up with the same coefficient. This coefficient then was confirmed by another analysis for other gauge groups by Amariti, Fazzi, and Segari, and it has also been given an effective field theory explanation as a log of the degeneracy of vacua in these two recent papers by Kasani, Komagorsky, and Ardehali and Murthy. So we are fairly confident on this log of n from the field theory side. From the gravity side, we have not yet been able to reproduce it, but I want to give you some insight. So from this near horizon geometry that I explained, some sort of more general way of looking at this, which essentially is Kerr-CFT with extra global U1 charges, you can compute the leading piece and of course match the entropy, but you can go ahead and look at logarithmic corrections in this framework and you get precisely the same result. So, and that extends also to the rotating string. So the main message that I have, there were a lot of computations, but let me make it. Let me try to crystallize what I was saying in the context of ADS. One has to be a little bit more careful about. There's yet not a universal formula or quantum entropy formula that we can use. So we go on cases by cases. In the case of ADS-4, there was some obstruction to moving to the near horizon region because there were zero modes, and in that case, of course, you have to look at the full space. In the case of ADS-5, there were no zero modes, and you can go to the near horizon, and the computation seems to agree on those 2 points of view. That's, I think, is sort of where this is pointing. I did not have time to talk about, so once you have a CFT2 description of the black hole that is reliable because there are no zero modes obstructing it, you can try to apply an analysis a la Kalam-Maldacena and get some insight into Hawking radiation, and that we did with Junyan. As I said, it's still outstanding to compute the log directly from type 2B supergravity, but there's some more progress. The question of higher curvature corrections, the other type of corrections that in my first slide will essentially ... I think that the proper, well, there's been interesting, exciting work by Bobiev, Charles, Christophe, and Reis, but perhaps I think the right conceptual home for those is the Wolf formula, which one can hope to get as a generalization of sense entropy formula. And I have some ongoing work on that. So I want to finish just by stating that, so ADS-CFT has de facto, right? Because we have a unitary description of black holes, solve many of the puzzles, but we have not seen the solution explicitly. And I think this is a very exciting time where some of these questions are being answered very explicitly. So thank you very much.
Great, thank you so much, Leo. Warm round of applause. Thanks. Well, I don't know if you wanted to keep your slides up in case
I can keep them up.
And you wanted to point to them, but
All right.
it's also fine to not do it that way. But okay, let's start seeing who wants to raise their hand first. Don't be shy. Okay, maybe I'll ask a question very quickly. Just to put things in context, this obstruction of building the quantum entropy function for the ADS black holes, is it related to the nature of the attractor mechanism in ADS?
I think for the quantum entropy formula, so I am a little bit ambivalent about this. So I think the quantum entropy formula is obstructed by really zero modes that that you can see in the higher dimensional ADS, but maybe not in the lower dimensional ADS description. The attractor mechanism, at least at the level of Bekenstein-Hawking entropy, everything seems to work fine.
Okay.
So it is when you try to say I have now not only well, I call it classical, but it's probably a misnomer. So the wall entropy seems to work from near horizon, but we have trouble with this other part.
Okay, so it's on the quantum. Okay.
Yeah.
Thanks. I'll keep on asking questions, but again. Oh, there, Sohar. Please go ahead.
Hi, Leopoldo. Thanks for the nice talk.
Sure.
Given, sorry that I cannot turn on the camera. I'm in the middle of a move. Given that in the field theory side, this log n can be explained by the degeneracy of aqua. Essentially, it's the same degeneracy that you find in a deconfined gauge theory. And wouldn't that mean that on the ADS side, that should also correspond to some flat connections, like different saddle points with some different flat connections that are very similar to the degeneracy of aqua that you find in any deconfined gravity dual?
Yeah, yes, I think that's precisely correct. So I think on the field theory side, now, again, thanks to this recent work on the effective field theory of the index, I think we understand that from different points of view. Also, just from the slightly more computational point of view, we have, if you look at it from Bethe-Ansat's approach, you can simply see that this is a degeneracy in the holonomies. So this part I think we understand. But what we don't understand is how it comes from type 2b supergravity, let's say.
I would think it's just the two-form gauge field that is the gauge field of the one-form symmetry on the boundary. There is a two-form gauge field in the bulk, which is the gauge field that corresponds to the discrete one-form symmetry on the boundary. And since the discrete symmetry in the boundary is spontaneously broken, that's where you get the log n from. It should correspond to some flat connections of this two-form gauge field.
I see.
Okay, I'll ask another short question since I don't see any hand raised and I'm tempted. So for the ADS5 case, you are imagining doing the computation in 10 dimensions, right? So
yes.
From ADS5 times S5. So in that perspective, the heap kernel is not going to be trivial. Like you'll get contributions from.
Yes, but that is true. However, if you actually sit down and try to do them, there is an amazing amount of cancellations. So I think, and I was secretly hoping for the answer, and the answer is very universal. I did not emphasize it, but it's true for any ADS5 black hole in ADS5 plus Sasaki-Einstein 5. So it's again very universal. The field theory we know is completely for many n equal 1 Kuiper gauge theories, is precisely the same value. So I knew it had to, well, I know it has to come from something perhaps along the lines of what Sohar just mentioned. So because let's say the the width coefficient that you want to compute is non-trivial, but because of the structure of the supergravity solution, I have seen an insane amount of cancellation. So it looks like all those cancel, and then you're left with one counting argument.
But is it important that the background is supersymmetric, or do you think it would also hold if the black hole itself is non-BPS? Because there were some also miraculous cancellations in 4D.
Yeah, no, I am aware, but I don't know. I don't want to. Yeah, I don't want to commit to that.
Okay. Thank you. So I think I don't see any more hand raised. So this is the last call.